Hello everyone, welcome to my channel VKS Chem Tutorial. In this video tutorial, I will discuss rearrangement to electron deficient nitrogen atoms. Rearrangement may be molecular rearrangement, may be rearrangement to electron deficient carbon atom, electron rich carbon atom, electron deficient nitrogen atom. In this video, I will discuss rearrangement to electron deficient nitrogen atoms. Important molecular rearrangement relating to electron deficient nitrogen atoms are Hofmann rearrangement, Curtius rearrangement, Lossen rearrangement, Schmidt rearrangement, and Beckmann rearrangement. I had already uploaded a video about Beckmann rearrangement. In this video, I will discuss the mechanism and important reactions of Hofmann rearrangement, Curtius rearrangement, Lossen rearrangement, and Schmidt rearrangement. Let us discuss Hofmann rearrangement first. This rearrangement provides an effective method for the synthesis of a primary aliphatic or aromatic amines from primary amides. By using Hofmann's rearrangement, a primary amide can be converted into an amine, maybe primary aliphatic amine or aromatic amine from primary amide. The mechanism of reaction involves the treatment of an amide with sodium hypobromate or bromine in alkali gives N-bromoamide, which reacts with base to afford a conjugate base within which rearrangement takes place to give an isocyanate. Now, the formed isocyanate may be isolated in anhydrous condition, or it can be converted into amine by aqueous workup. See the mechanism. First of all, the amide will be attacked by the strong base like sodium hypobromate or sodium hydroxide in bromine. The hydroxide ion capture a proton from this amide to form this anion. Then bromine attacks nitrogen to form N-bromoamide, and then the hydroxide group of alkali capture this proton forming these anions. It rearranges or rearrangement takes place here, and so the alkyl group from this carbonyl group migrates to nitrogen with the elimination of bromine. With the elimination of bromine, nitrogen becomes electron deficient. Thereby, this alkyl group migrates to this electron deficient nitrogen atom. And this rearrangement step is the right determining step, whereby the isocyanate is formed. The formed isocyanate on hydrolysis will be obtained the product amine, primary amine, with the elimination of a carbon dioxide molecule. It is the actual mechanism involving Hofmann's rearrangement. Often this rearrangement is known as Hofmann's degradation reaction because the formed amine or the product contain one carbon atom less than the reactant amide, and hence it is an example of degradation reaction. Okay, if this reaction is carried out in alcohol, urethane is obtained. If the reaction is carried out in alcohol, the formed isocyanate reacts with alcohol forming urethane. Sometimes urea derivative is also obtained by reacting the formed primary amine with this isocyanate. Thereby urea derivative is formed in some cases. In aryl amides, that is when the migrating group is in aryl, that is when the migrating R group is aryl group, then the rate of Hofmann rearrangement gets increased by the presence of electron releasing substituent in the para position of the aromatic ring. For example, in this case, it is This ring is the migrating group. Aromatic ring is the migrating group. You can see a para-methoxy group present in this benzene ring. Methoxy group is an electron releasing substituent. Then in the right determining step, see the electron releasing group releases the electron towards benzene ring and the rate of reaction gets increased. Then the benzene ring migrates towards nitrogen in the right determining step, forming this anion, dipolar ion. Then bond breaking takes place by donating the electrons from oxygen of the carbonyl group to the carbon atom. Thereby electron shifts towards methoxy group takes place, then forming this paramethoxy isocyanate, paramethoxy aryl isocyanate. Then, as in the usual case, hydrolysis takes place, forming paramethoxy aniline. Okay, see the migrating aptitude of the aryl group decreases in this order when these groups are present in the para position of aryl group. Methoxy greater than methyl, greater than hydrogen, greater than chlorine, which having electron withdrawing influence, then nitro group, that is also electron withdrawing group. Now let us discuss the next rearrangement, Curtius rearrangement. This rearrangement describes the transformation of an acyl azide into isocyanate by decomposition on heating and its application for the synthesis of primary amines, urethanes, and ureas as presented in Hofmann's rearrangement. In Hofmann's rearrangement, an amide is converted into an isocyanate, while in this Curtius rearrangement, an acyl azide is converted into isocyanate. Okay, the rest of the reaction is similar to Hofmann's rearrangement. For example, on hydrolysis of the isocyanate, we will get amines, primary amine, as in the case of Hofmann's rearrangement. In this Curtius rearrangement also. See the mechanism. First of all, we have to prepare acyl azide. It is acyl azide. It is prepared from acid chloride by treating with the sodium azide. We will get this acyl azide. This acyl azide on strong heating, rearrangement takes place to form the isocyanate. Isocyanate. As in the Hofmann's rearrangement, this isocyanate on hydrolysis, we will get corresponding primary amine. Then on treating with an alcohol, we will get urethane. And on reacting with the primary amine, we will get urea derivative as in the Hofmann's rearrangement. Right. See the mechanism involving the formation of acyl azide from acid chloride and the decomposition of acyl azide to form isocyanate. Here acid chloride reacts with the sodium azide, forming, see, nitrogen attacks the electron deficient carbon atom of the carbonyl group. Thereby this anion or this intermediate is formed. Then sodium chloride is eliminated from this intermediate. We will get the acyl azide. From this acyl azide, nitrogen molecule is eliminated like this. Nitrogen molecule is eliminated, forming corresponding isocyanate. Okay. The next rearrangement is Lossen rearrangement. It involves the ester of hydroxamic acid when it is decomposed in presence of a base to form isocyanate. You can see in all these three reactions, Hofmann rearrangement, Curtius rearrangement, and Lossen rearrangement, all these rearrangements, you can see isocyanate is the intermediate, or the formation of isocyanate is important. The reaction is normally carried out in aqueous or alcoholic solution in which the isocyanate converted into an amine or urethane. It is known as Lossen rearrangement. See, the difference with the Hofmann rearrangement is the loss of carboxylate ion instead of bromide ion in Lossen rearrangement. In Lossen rearrangement, instead of bromide ion in the Hofmann rearrangement, here carboxylate ion is lost. See the reaction. It is an ester of hydroxamic acid, which on treating with a base, water is eliminated to form amine, primary amine, as in the case of Hofmann's rearrangement. Okay, then see the mechanism. It is the ester of hydroxamic acid, which on treating with a strong base capture a proton from this ester of this hydroxamic acid, then whereby forming this anion. Then rearrangement takes place with the elimination of a carboxylate ion. There is the difference of Lossen rearrangement from Hofmann's rearrangement, as we discussed. Then rearrangement takes place. This alkyl group migrates to this nitrogen, forming the isocyanate. This isocyanate hydrolysis forming primary amine. Okay, that is a mechanism of Lossen rearrangement. Then the last rearrangement in this video, Schmidt rearrangement. See, carboxylic acid reacts with the hydrozoic acid in presence of concentrated sulfuric acid to give acid azide, which is present in the form of conjugate acid, eliminates nitrogen to afford isocyanate that could be converted into amine, as reported in the Hofmann's rearrangement and other rearrangements such as Lossen or Curtius rearrangement that we had already discussed. For example, see this acid, carboxylic acid, which on treating with the hydrozoic acid in presence of concentrated sulfuric acid, amine, primary amine is formed. Then the carbonyl compounds also undergo Schmidt reaction. Carbonyl compounds such as aldehydes and ketones, when treated with hydrozoic acid in presence of sulfuric acid, Schmidt reaction takes place. For example, see, it is an aldehyde which on treating with the hydrozoic acid in presence of sulfuric acid, this intermediate is formed. Then which on hydrolysis, it is an amide which on hydrolysis gives formic acid and primary amine. Similarly, if we treat a ketone with hydrozoic acid in presence of sulfuric acid, this substituted amide is produced, which on hydrolysis we will get the corresponding acid and primary amine. See, one of the important difference between the Schmidt rearrangement and Beckmann rearrangement is Beckmann rearrangement is stereospecific in nature, but Schmidt reaction or Schmidt rearrangement is not. Same product will be obtained if we treat, for example, cyclohexanone with hydrozoic acid in presence of concentrated sulfuric acid. We'll get caprolactam. The same product, caprolactam, will be obtained if the cyclohexanone is treated with hydroxylamine followed by acidification or acid workup in the case of Beckmann rearrangement. And so we can say both the Schmidt rearrangement and Beckmann rearrangement gives caprolactam on treating on taking cyclohexanone. Cyclohexanone in Schmidt rearrangement on treating with the hydrozoic acid and sulfuric acid, we get caprolactam. But in Beckmann rearrangement also, cyclohexanone on treating with the hydroxylamine followed by acid workup, forming the same caprolactam. But Beckmann rearrangement is stereospecific in nature, but Schmidt rearrangement is not. That is the basic difference between Schmidt rearrangement and Beckmann rearrangement. See the mechanism of Schmidt rearrangement. First of all, carboxylic acid gets protonated in presence of hydroxamic acid, forming protonated carboxylic acid. From this, water molecule is eliminated to form this oxonium ion, which rearranges to form the acyl cation, which reacts with hydroxamic acid, forming the azidoketone, protonated azidoketone. And from this protonated azidoketone, a nitrogen molecule is eliminated to form a protonated isocyanate. And to this protonated isocyanate, water molecule is added, thereby forming a protonated carbamate. From this protonated carbamate, proton is eliminated, or protonated carbamate is deprotonated, followed by the elimination of carbon dioxide, forming the final product, primary amine. That is the mechanism involving Schmidt rearrangement. See, it is the mechanism if the Schmidt reaction taking place with a ketone. This ketone, in presence of hydroxamic acid, first protonated, and then with hydroxamic acid we will get this cation, and it is protonated to form this protonated alcohol. A water molecule is eliminated from this protonated alcohol, forming this cation. Then deprotonation of this cation, forming this cation, from which a nitrogen molecule is eliminated with the migration of alkyl group. That is the actual rearrangement, forming this ion. In presence of water, it gets converted into this protonated enol. Then deprotonation takes place to form this enol, which tautomerizes to produce substituted amide. And this substituted amide, on hydrolysis, we will get the final product, carboxylic acid and primary amine. Okay, that is the mechanism of Schmidt rearrangement if we take a ketone. I have already discussed the Hofmann's rearrangement, Curtius rearrangement, Lossen and Schmidt rearrangement with their mechanism and important applications. With this, I conclude this video. Thank you for watching. Thank you.